Hey functions. So, happy Monday, Tuesday, whatever day you're watching this. This lesson gets the title Linear Programming. And what linear programming tries to answer is the following question, or questions similar to. I want you guys to find coordinates x, y that maximize the equation or the value m equals 4x plus 6y. Alright, I want you to maximize that. Before I continue, I totally realize that this is not how you spell equation. My bad. But think about how to maximize this value m. If you have no idea what I'm talking about, because that doesn't really make sense, just make x and y as big as possible, which doesn't make sense in its own right, that's because I have not told you the entire equation. We're not just trying to maximize m for any x and y. We have constraints. So here's the real question, right? We need to maximize 4x plus 6y such that x is greater than or equal to 0, y is greater than or equal to 0. Negative x plus y must be less than or equal to 7. X plus y must be less than or equal to 27. And 2x plus 5y must be less than or equal to 90. So what is this? This is a system of inequalities. That is what we're doing here. System of equations, just kidding, system of equalities. So this set of inequalities is called the region of feasibility. Why is it called the region of feasibility? Well, we need the x and y that we choose to maximize this thing to be contained in all of these system of inequalities, but we also can graph these inequalities, and we can look at the intersection region, and the coordinates within that region are the feasible solutions. And our goal is to choose the solution set, the x and the y that maximize 4x plus 6y. So let's go ahead and graph these inequalities and see what that region looks like. All right, so to graph these, I'm going to do what you would normally do when graphing linear equations. I'm going to solve for y and sketch the line that all of these make, and then look at the contained area. So let's go ahead and solve all of these for y. The first one is still just, this is a vertical line. We're going to have y must be greater than or equal to 0, horizontal line. Cool. Negative x plus y is less than or equal to 11. That's going to become y is less than or equal to x plus 11. The second one, x plus y is less than 27. That's going to become y is less than or equal to negative x plus 27. And the final one, 2x plus 5y is less than 90. That's going to become y is less than or equal to negative 2/5 x plus 18. All right, and now I want to graph all of these and see how these intersect. So I'm going to give a whole new page to the graph of this. So let's go ahead. All of these are going to be found in the first quadrant. So I'm going to go ahead and graph myself a first quadrant here. Cool. Let's go ahead and graph them. We got x is greater than or equal to 0. that's going to be just all of this, everything to the right of the y-axis. Same thing with the y, so those lines, I'm going to go ahead and change the color. So we got x is equal to 0. We got y is equal to 0. The next one, we got y is equal to x plus 11. So let's go ahead and say like this right here is 11. All right, we're doing a sketch. I'm not going to actually draw this to scale. So let's go ahead and say that's 11. So y equals x plus 11. That's going to look like this thing. Cool. I'm going to go ahead and write y is equal to x plus 11. So I remember that that is that line. We have y is less than or equal to negative x plus 27. So that's going to be like up here. Cool. And negative x, we're going to have a negative slope. And I'm going to go ahead and call this one right here y equals negative x plus 27. And our final equation, negative 2/5 x plus 18. So a y-axis, y-intercept of 18. That's going to be like somewhere in between. And we're going to have a slope that is slightly less steep than negative 1. So it's going to look kind of like this, but it is still negative. All right, I'm going to actually back up a little bit. All right, and this is our y equals negative 2/5 plus 18. Cool. All right, so we've graphed these. All right, we have some intersection points. These go this way a little bit more. We have this point right here. And let's look at the region where these inequalities intersect. All right, so y must be less than all of these things. So if I start to think about the region where x and y agree with all of these inequalities, like this little tiny triangle here, that is not going to work, because while it is less than x plus 11 and it is less than, what is that? It's less than negative x plus 27. It is not less than negative 2/5 plus 18. So I want to go ahead and get rid of that. So I need things less. I can't use anything outside of the first quadrant because of those first two restrictions. So it's looking like the region of feasibility is this pentagon right here, right? This intersection point, this intersection point, this intersection point, boom, boom. I'm gonna go ahead and like highlight this pentagon. This is our region of feasibility. Right? These are the x and y coordinates that agree with all the inequalities. Now the goal is to see what coordinate within this region maximizes 4x plus 6y. All right, so let's start looking at possible solutions. So how about this right here? I don't know what it is, but could this point right here be the solution? Could the solution to this problem be in the interior of the pentagon? I want you to think about that for a second. Go ahead and pause the video, think. But I'm going to go ahead and justify why this could not be the solution that maximizes this. Why is this? Because we can move left and make x bigger, thus making this quantity bigger. Or we could also move up and make y bigger, thus making this quantity bigger. So this point cannot be the solution. If this was negative, or this was negative, moving left or down would make this solution bigger. So with a kind of a loose justification here, the solution to this problem, maximizing m, cannot be in the interior of the pentagon. What does that mean then? It must be on the exterior of the pentagon. So we need to start looking at the points on the exterior. Right? That point in the middle cannot be the solution. The next thing I want to look at is, can this be the solution right here? Could that be the solution? I want you to pause and think about why this could or could not be the solution to this problem, maximizing m. But with that said, the answer to my question here is no, this cannot be the solution to the maximization problem, because I can move up or down this line, and with this line, what I care about is the slope. So if I move down this line, my x is getting bigger. My y is getting smaller, but how are they getting bigger and smaller? As I go down, the x is increasing the same amount as the y is decreasing. So as I increase x, let me go ahead and get rid of these negative signs I had previously written. As I increase x, for every increase in 1x, I am getting 4 more units. But every time I increase 1x, I am decreasing 1y, so I'm losing 6 units. So as I move down this line, I'm increasing 4, but losing 6. So I am in fact decreasing as I move down this line. Likewise, as I move up the line, I'm decreasing 4 for every unit, but I'm increasing 6 because of the y going up 1. So moving up this line actually results in a larger m value. Moving down the line results in a smaller m value. So none of these points can be the answer to my solution, because I can always go up this line a little bit more until I get to this point right here. All right, and this leads me to my final assertion. The solution to a linear programming problem must be one of the vertices of the region of feasibility. So let me go ahead and write that down. The solution to a linear programming problem must be a vertice let me actually say the correct grammar, a vertex on the region of feasibility. All right, so that's a little theorem for you. All right, so let's actually solve this problem now. So I'm going to go ahead and redraw the region of feasibility on our new page because it was getting a little messy. All right, so we had a line going from the point right here, 0, 11, with a slope of 1. We had a point way up here at 0, 27 with a slope of -1. All right, so we had an intersection here, but we didn't care about that intersection. And then we had a point here at 0, 18 that had a slope of -2/5. So a little bit less than -1 in terms of steepness. All right, and then we had an intersection here, 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 and here. So those are the possible solutions to this maximization problem. Right, here is our pentagon. We have 5 constraints, so we have 5 lines, so we have 5 sides. All right, and we need to figure out on this pentagon which vertex gives us the best. There's some that we can rule out immediately. This one here, 0, 1, we can rule out immediately. Sorry, 0, 0, because we can increase x and we can increase y, thus increasing that objective function. By the way, that's the name we give this. We give it the name objective function. Not the most important thing, but vocabulary comes in handy. All right, we can get rid of 0, 11 because we can increase both x and y. 0, 18, that is a possibility. Sorry, no. 0, 18 is not a possibility. It's not on our region. But this intersection point right here is a possibility. So I'm going to go ahead and highlight that one in its own color. That's a possibility. This one's a possibility. We've already canceled this one out, so this one does not work. We canceled this one over here out because we can move up this line, thus increasing 4x and 6. Thus increasing the 6 and losing the 4, but ultimately gaining 2 for every unit moved. All right, so we need to look at this and this, so we just need to figure out where their intersections are and then figure out which one's better. So let's go ahead and do that. All right, so this line right here was x plus 11. This line right here is negative 2/5 x plus 18. So we're going to just go ahead and solve this. We're going to get, what is that? 7/5 is equal to 7/5 x is equal to 7. Go get rid of the 7's, multiply by 5, x is equal to 5. And because of that, y is equal to, what is that, 16? Cool. All right, so that's one of our solutions. This coordinate right here is 5, 16. All right, let's go ahead and solve the other one as well. So I'm just going to go ahead and continue to use this page. Awesome. So the other equation was, we want to look at this intersection. So we have negative x plus 27, and we have, once again, negative 2/5 x plus 18. This time I'm going to add x, so that's going to become 5x plus negative 2x. That's 3/5 x. Subtract 18, that's going to be 9. Get rid of the 3, so this becomes a 3 multiplied by x. X equals 15. And because of that, y is equal to 27 minus 15 is 12. So this coordinate right here is 15, 12. Which one's better? There's several ways you can think about it. I'm just going to go ahead and plug them in. So just going to do that real quick. So for here, m is equal to 4 times 5 plus 6 times 16. That is equal to 20 plus 60, 96. 20 plus 96. That is 116. And then down here, m is equal to 4 times 15. I already have a sense that this one's going to be a little bit bigger, but I'm going to double check. I'm going to just do the maths. 60 plus, what is that going to be? 60 plus 72. 60 plus 72 is 132. All right, so there it is. All right, 15, 12. All right, we wanted to maximize 4x plus 6y. All right, we had a set of constraints which we call the region of feasibility. Because of that, we were looking within this region and figured out that a vertex must be the solution. Right? And in checking the vertices, 15, 12, 15, 12 maximizes m. Woo! All that calculation actually doesn't matter too much. I could have just established that this point cannot be the solution. Which way is going to increase? I just didn't feel like it because I didn't like the slope negative 2/5. But the slope negative 2/5, that says as I move to the left, or let's do the right. As I move to the right 1 unit, 2 units, I'm going to be going, as I move to the right 5 units, I'm going to be going down 2 units, which means as I move to the right, I'm going to be gaining 20. Sorry, yeah, I'm going to be gaining 20 and losing 12. So every time I move to the right, I gain 20, lose 12, so I gain a net of 8. So that is why this point right here must be our maximum point. But I just like to plug them in. I like to get rid of the easy ones and then just plug in the last few tricky, annoying ones. All right, so that's the topic of linear programming. We're trying to maximize a value with a set of constraints. Those constraints are inequalities. But yeah, that's why this kind of falls in the system of equations matrices unit. It is a system of equations in a way, inequalities. Yeah, a little bit of geometry for you there. I will see you guys in the next video. All right, linear programming.